Whether or not you realized it, with the derivation of the stream power law, we started entering what I think of as the fun part of the semester. The part of the semester where we've fought our way through fluid mechanics, where we've worked through the erosion of rivers and diffusion of hill slopes and other geomorphic processes with which we're concerned. And now we're ready to actually start applying these to understand how whole landscapes evolve. Now, of course, I like to think that the rest is fun too, and I personally love fluid mechanics, but I'm willing to wager a bet that some of you guys share my opinion, and some of you actually might appreciate just having a fairly simple master equation that you can use to explain the form of a landscape. So let's get started. So what we want to know is an equation that relates the change in elevation over change in time to something. And this is going to tell us how a landscape evolves, because evolution of a landscape is the change in elevations. So landscape, we can think of this as terrain, or equivalently topography. And this is time. So it's the evolution of topography over time. You know, it took me until I started making these videos to realize that I wish I could write faster with a good hand. But that's one of these aspirational things, and I'll just chuck that into the future. So dZdt is going to be something, and this is going to describe the evolution of a landscape. So let's think about this. We have a couple rules, and so we talked early on in the semester about the evolution of a hill slope. So we're going to have something like dz over dt from a hill slope being equal to some term k sub h times d squared z over dx squared. So this is hill slope diffusion. And just to make sure that you are all well aware, this ignores landslides or any mass wasting event. Right, this is only about this kind of gradual soil creep, and of course the soil creep is going to get faster as the hill slope gets steeper, but it has no critical angle at which it starts to fail. So strictly this isn't correct, but assuming that we keep kind of gently sloped hill slopes, this isn't so bad, and it's definitely a simpler equation. So let's run with it. Next we have dz over dt of the fluvial system. And this is going to be related, in this case, to bedrock erosion. I'll actually list that at the right. And this is going to be equal to this k term. And so I'm going to call this just big K, a to the m, s to the n. And this is all from, as I mentioned, bedrock erosion. Or incision. And so those are two terms. And now I'm just going to add one more, which is dz over dt tectonic. And that is just going to equal to a constant, u. Uplift, hence the u, if it's positive, or subsidence, if it's negative. So, with landscape evolution, we're going to do the simplest thing, the stupidest thing possible, but it's going to work. What we're going to do is to say that dz over dt of the landscape as a whole is just equal to dz over dt from hill slope processes plus dz dt from the fluvial processes. And actually, I forgot to mention, so this is supposed to be the erosion rate from the fluvial processes, so there should be a big minus sign out here. I apologize for that. So in that case, we're going to go minus k a to the m s to the n. And here, this minus sign here is relating to the fact that we're removing material when we're incising. If we had the slope as something that would have a negative sign if we're going down slope, and n were 1, then we could just use a plus and use slope in that place. However, it's actually easier right now to just treat this as a minus sign and allow slope to be the absolute value of the steepest down slope direction. And then we're going to add in uplift, because if there's uplift, the whole landscape becomes higher. And of course, that uplift can be a function of space, as can any of these other values. So after that, let's well, actually that's funny. What I really meant to do, and let me just erase this because I think I got a step ahead of myself. What I really meant to do is take 2 steps to go through this. And the first one, I would have plus dz over dt fluvial plus dz over dt tectonic. But I just got so excited that I just wanted to jump to the end and show you guys what the full equation is. So if I combine all these together, then what I have is dz over dt is equal to k sub Hillslope times d squared z over dx squared plus, or rather minus, k times the drainage basin area to the m, the slope to the n, and just so we can have something in here, I can mention that the slope is going to be the absolute value of dz dx. Plus uplift. So then just to write this out once more, to use proper partial derivatives everywhere too, so dz over dt is equal to k sub h d squared z over dx squared minus k a to the m, absolute value of dz dx to the n. And it's important to note that this drainage basin area is something that we're going to have to calculate from a digital elevation model based on the number of cells that are sending water, so the number of pixels in that digital elevation model that are sending water via their slopes and drainage areas downslope into a particular cell on the map. And then we're going to add in this uplift term. So altogether, this is the simplest possible that I know of master equation for landscape evolution in a system that involves channels, hillslopes, and tectonics. So this is the simplest landscape evolution equation. And so there you have it. This is the core equation that's written into computer models and geomorphology, and it's also an equation in which I need to make sure that this too is properly seen. So from this equation, if you can write this equation in 2 dimensions, for example, you can actually then create a full landscape evolution model that has dynamic drainage basins and channels and hill slopes.